Okay, in part 2, we'll look into formal logic. We do this because we'd like to be able to do reasoning, and in AI in particular, we'd like to be able to do reasoning or inference automatically. This here an example of an inference going wrong. Of course, our idea will be to do valid inference. Okay. Before we actually look into what formal logic is, I'd like to give you a broader picture about how formal logic and the idea of knowledge representation is actually situated within a wider landscape of AI. And there is two schools of thought, essentially, two schools of thought, or two camps in AI. One's called symbolic approach or symbolists, and the other are the connectionists. So it's symbolism versus connectionism, essentially. Now, symbolism is about using symbols to formalize knowledge. And a symbolist actually believes that the external world can be represented using symbols down to its very details, and that inference then amounts to manipulating these symbols to derive new symbols, which then are essentially representing new knowledge, right? So intelligent reasoning, according to the symbolist, is actually amounting to inference. And as you can imagine, symbolic logic or formal logic is actually in the heart of the symbolic approach to AI. But there is an alternative. The alternative is connectionism. A connectionist believes that the mental states and intelligent behavior emerges from interaction of a large number of relatively simple but highly interconnected processing units. A case in point being a neural network, where you would have a large number of simple processing units called artificial neurons, and they are interconnected, and based on the weights that you have in between these neurons, they would eventually turn out to do some intelligent mapping of input to output, right? So that then is the other school of thought, connectionism. In what follows in this lecture, as well as in the next week's lecture and the week after that, we'll stick essentially to the symbolic approach, the logic-based approach to AI. But it makes sense at the time being for us to realize that there is an alternative, the connectionism. And yeah, maybe to give you an example of how a symbolist approaches a problem versus a connectionist, think of an apple as a concept. And in the world of symbolism, an apple would be represented, so there is an apple here, would be represented in terms of a structure, and the structure would be mapped or described via some symbols. So if you need to define an apple, you would probably want to talk about its origin, the structure of the apple, and then decompose it further into a body and the stem. And you might want to talk about the kind of an apple and how it fits into the taxonomy of edible things. And this then is in contrast to how apple would be represented in connectionist model, right? But there is no symbols at all. There is only some neurons here, the circles here, and some connections between them. And then there is weights on these connections that signal how strongly these neurons are connected. So you see there is no symbols here, no structure, no definition of a kind or an origin of an apple, no properties explicitly being described. Everything actually amounts to a set of weights, essentially numbers, between a set of nodes, right? Okay, as I said, we are now for the time being focusing on the symbolic approach to AI. And I also like you to be aware of the fact that the symbolic versus connectivistic approach, the struggle between the two has a long history, actually going back to the very early days of AI. in the very beginning, and we're talking here in the years during and immediately after the Second World War, the connectionist approach was the dominant approach. I guess this also makes sense since, the human brain is actually a working system and it's a model that we sort of strive to replicate. And in 1943, there was the first artificial model of a neuron by McCullough and Pitts. So this then spurred a lot of interest into doing connectionist approach to AI. But somewhere around 60s here, it turned out that there's things that the neural networks of that time were not able to do, and this then basically started the area of the dominance of symbolic approaches. So most of the researchers abandoned doing any research on the neural networks, and work has shifted toward, the focus has shifted toward symbolic approaches to AI. Then again, in mid-90s, the forces have shifted again, and the statistic-based approach actually became the dominant approach. And you can think of statistic-based AI as a flavor of connectionism, essentially, especially with very performant machine learning algorithms. And later, we don't have this here, but nowadays in 2020, we have machine learning based on neural networks and deep learning, which is again a nice prominent example of connectionists approach to AI. So the point here is that basically the trends shifting from symbolism to connectionism depending on many factors. And now if you ask yourself, what's the ultimate way to go, and what's going to give us the AI that is actually solving the AI complete problems, I would actually put my money on a hybrid approach of some sort that combines symbolic and connection and connectivistic models. But we'll still have to wait for a while for this to happen. Okay, now let's go back to symbolic approach, and let's now try to talk about the about the formal logic a bit more. Now, formal logic, or also known as symbolic logic, is actually a branch of math concerned with mathematical concepts that are expressed using formal logic systems. And as the whole body of math essentially builds on mathematical formalisms, which essentially are built on symbolic logic. These systems, from the perspective of AI, these formal logic systems will allow for abstract reasoning, and that's what we are after here. Symbolic logic has a very actually long and interesting history, dating back to, well, there's many attempts, but I guess one prominent is that of Gottlob Frege, the German philosopher and logician, and his work on the so-called Begriffsschrift, which essentially is a formal language and is the precursor of what we now call the first-order logic, or the predicate logic. And as you can see, this was the end of the 19th century, essentially. Well, Gottlob Frege was an optimist in the full sense of the word, and his goal, his life goal, which he did not accomplish, unfortunately, was to formalize the whole of human knowledge in a system of formal logic. And one thing that he has developed then was this formal language, and you can see the depiction of it here. It might seem to be quite cryptic, but if I now tell you that this is just a flavor of what we nowadays have as predicate logic, then I guess it would make a whole lot more sense. So, for example, the line that is intersecting with a horizontal line, a vertical line intersecting with a horizontal line, is actually meant to mean implication. So, for example, this formula, and this formula and this formula all imply this formula, right? And these things here are the quantified variables. So this essentially means for all be in these formulas and for all n's in these formulas. And these little lines here lingering below horizontal line are actually negations. So this can be mapped into a predicate logic formula, and this actually was the motivation and the foundation and the basics for the predicate logic or the first order logic as we have it nowadays. Okay. Now every formal logic system consists of three components, and the first component is the basic one is the syntax. Syntax describes the structures, and these structures essentially constitute the language of logic. It defines the formal rules for how to build strings of logic, right? The logic formulas. Once we have syntax defined, the next step is to talk about what these formulas actually mean, and this then is in the purview of semantics. So semantics describes the meaning of language constructs, and for example, this now depends on how elaborate the semantics is for a particular formal logic system, but typically you would want to talk about which structures are true and which are false, or what is the relation between language elements and objects from the external world, for example. And the third component then is to have some way of deriving new knowledge, and this goes under the name of proof theory. Proof theory defines the mechanisms for doing inference, for deriving new conclusions based on the existing premises. Okay, and we'll be needing all these three components in an AI system. Obviously, we need syntax to be able to express things. But these things need to mean something, so we need semantics. And once we have done this, then we'd like to infer new knowledge. So 1 and 2 serve to represent the real world knowledge, whereas 3 serves to derive new knowledge using the mechanisms of inference. Okay, hopefully this made sense. Now let's talk about expressivity of logic. It turns out there is many kinds of logic out there, and then they differ in the three components that we just introduced. The main difference between these logics, at the end of the day, amounts to the level of expressiveness. So there is logics that are more, and there is logics that are less expressive. By expressive, I essentially mean what are the things that can be said in that very logic, right? So maybe I can talk about things being true or false, but maybe I can go into more details and talk about parts of things and how they relate to each other. Or maybe I can go into even more details and talk about time and how time changes the environment, for example. Now, obviously, it would make sense to go for high expressivity of a logic system, because if I have a highly expressive logic system, then I'm able to talk about a lot of details in the real world. So high expressivity allows for a more detailed description of the real world, which basically means that you can maybe also do more detailed inference, right? Because you are able to talk about details, so then the details would make a difference, right? When you decide about the next action to carry out, right? Well, but there is also downsides of high expressivity in logic. The first is a technical one, so to speak. If I have a more expressive system, then I'll need a more expressive syntax, because syntax need to support this. I need to be able to say very detailed things, and then I need to have the devices in language to do so. And then in turn, if my syntax is more complex, then these things have more complex meaning. So the semantics has to basically correspond to syntax as well. So the semantics needs to be more complex as well. And finally, if the syntax complex and semantics as well, then my proof theory will have to be complex as well, because I need to derive new knowledge, and the proof theory will be able to handle the complex syntax and the complex semantics, right? So that's, I guess, one downside, a technical one. But there is a more substantial downside to highly expressive logical systems, and it's that at a certain point, as you increase the expressivity of your system, you actually lose the ability to infer things or to prove things within that very system. And that's what we call undecidability. And that's actually quite a grave problem. So ideally, I would like to have a logic that is not undecidable, which is to say a logic that is decidable. And if it's decidable, then this means that it's possible for me to check the validity of any formula, which essentially just means I can infer things. Okay, I can infer new knowledge. Now, if the logic is too expressive, then it's going to at some point lose the decidability, and this I will face the situation where I cannot actually prove some of the things. I will then not be able to infer some things, and I'll not be able to tell if these things actually hold or do not hold. I'll just be left without an answer in this case. So you see, I'd like to be able to express a lot of things, to have a highly expressive system, but then again there's downsides to high expressivity. So in practice, when we build AI systems based on logic, we are facing a dilemma here, a trade-off between expressivity and decidability. So in principle, the more expressive a logic is, the fewer the number of things that I'll be able to prove in that logic. At an extreme, very expressive logical systems will not be decidable, whereas systems that are not very expressive will actually be decidable, but then again they cannot really express much. So in the extreme they will be worthless, because there is not many things that I can tell using these systems. So as I said, in practice, we are trying to find a sweet spot between expressivity, high expressivity, and decidability. And the two kinds of logics that we're going to cover today, the propositional logic as well as the first order logic, actually strike a good compromise between expressivity and decidability. Okay. Let's just make a quick tour through the different kinds of logics, the most popular ones out there. There's the propositional logic, also known as sentential logic, and that's the simplest kind of logic, and we're going to look into that next. The next step would be toward a more expressive system would be the first order logic, also known as predicate logic, or FOL. So FOL is more expressive than propositional logic. So there's things that I can say in first order logic that I wouldn't be able to say in propositional logic. But then again, there's going to be a price to pay in terms of losing decidability. There is also more elaborate, more expressive kinds of logic, like temporal logic, for example, for expressing time, or description logic, commonly used for knowledge representation in AI based on ontologies. Then there is fuzzy logic. Fuzzy logic is actually quite interesting. Fuzzy logic allows me to talk about the different degrees of truth, acknowledging for the fact that it's not a case that I can be definitely certain into some things being true or false. And fuzzy logic is also one formalism that we're going to cover in the course, but in the second half of the course. But there's more. There's model logic, for example. There is systemic logic that is used to describe the mental states of, say, intelligent agents, and what they believe, or maybe what they believe about what I believe, or what they believe I believe about what they believe, and so forth. Okay, so these logics here shown in boldface are the three formalisms that we are going to cover in this course, and today we'll cover the first two, and as I said, in the second half of the course we talk about fuzzy logic. Now, expressivity can be broken down into two components here, the so-called ontological commitments and the epistemological commitments. And I like to introduce these two concepts because they are also kind of useful. So let's talk about ontological commitments. First, let's talk about ontology. Well, ontology is like the hardcore philosophical concept. It is the branch of philosophy or metaphysics, to be more specific, concerned with the nature of what exists and what is the reality. So what is existing here actually, what's not. and the question of what entities exist and what are the relations between them. Now in AI, when we talk about ontological commitments, then essentially what we mean are the assumptions about what exists and what doesn't exist in the world. And of course, we are after modeling those things that we assume are existing, right? So for example, in propositional logic, we would assume that the world consists of facts, and these facts are either true or false. And there is nothing else that we assume. It's only, the world is actually a set of facts, which, each of which can be true or false. Unlike, for example, in temporal logic, where we would additionally assume that the world is actually consists of some points in time that are put in perfect ordering, in a total order, and this basically, describes the flow of time, for example. Okay. Oh, by the way, in ontology, the term is overloaded in AI, and there's yet another meaning in AI, which essentially means a formal representation of knowledge within a domain, but we'll not look into that. Now, the other the other aspect of a formal system that indirectly defines its expressivity level is the epistemological commitment. So, first, epistemology is again a branch of philosophy, but this one is concerned with knowledge, the scope of knowledge, the sources of knowledge, and the limitations of knowledge. And then in AI, when we talk about so-called epistemological commitments, then essentially these define the possible states of knowledge, right? So ontological commitments are basically telling us what we think there exists in the world, whereas the ontological commitments are telling us what we think we can know about what exists in the world, right? So, for example, in propositional logic, the epistemological commitments are such that each fact can be either true or false, and there is nothing in between, right? So it cannot, for example, be partially true or uncertain or unknown, right? Or just believed by some people but not by others. There's other kinds of logics that actually allow for epistemological modalities, like different levels of knowledge. And fuzzy logic is, I guess, the simplest example, where you would allow for a certain fact to be sort of true but not entirely true, and so forth. Okay. Cool. And now in the third part, we'll talk about the simplest logic of them all, which is the propositional logic. Stay tuned. Or not.